Okay, objective 6A, we are finding asymptotes. We'll be focusing on vertical asymptotes and horizontal asymptotes in this lesson. Eventually, the next lesson, we will also be looking for slant asymptotes. Now, vertical asymptotes are found by looking for the real zeros, not the imaginaries, but the real zeros that are in the denominator of a rational function. If a real zero in the denominator does reduce out, it is no longer a vertical asymptote. It will be a hole in the graph, and we've actually dealt with this situation before. You've seen some graphs where there's a hole in the graph and the limit existed because the graph was approaching the same hole from both sides, and that was the limit as x approached some constant, and we've seen that sort of thing before. Horizontal asymptotes are found by taking the limit as x approaches infinity. We just did that on our last lesson, and so hopefully we're very good at that at this point now. And so let's go ahead and try to find the asymptotes here. So I've got a few sample problems of that. So find all the asymptotes, and we're talking about equations of asymptotes, not just simply numbers. And we're also going to do x-intercepts as well, because that's part of ultimately what we're doing, which is graphing the rational function. So number one here, f of x equals 1 over x squared plus 2x. And factored form for the denominator is a good thing. So x times x plus 2, we can see that nothing reduces, and we have zeros of 0 and -2. So, vertical asymptotes, VA for short. Now, it's a vertical line, really, is what's going on, and so every vertical line we know is x equals. So x equals 0 and x equals -2. No, you may not just simply write x equals 0, comma, -2. Yes, you must write the two equations separately. Horizontal asymptotes, HA for short. Taking the limit as x goes to infinity. Now, we're not trying to be all formal and everything. It should be very quick. You look at the function, and you take the limit as x goes to infinity. Does it exist? Well, this one's bottom heavy, so yes, and every time it's bottom heavy for limits as x goes to infinity, it's 0. So, and it's a horizontal line, so y equals 0. So as far as vertical asymptotes, horizontal asymptotes, yes, it's very quick and easy potentially. Now, also asking for x-intercepts, and remember that x-intercepts are where y equals 0. So if I plug in 0 for the y, in other words, this fraction equals 0, well, if I cleared the fractions, if I multiplied both sides of the equation by x squared plus 2x, wouldn't we get 1 equals 0? Is that true? No. So if you have just a single fraction equaling 0, the only way a single fraction equaling 0 is if the numerator equals 0. Can 1 equal 0? No, there are no x-intercepts for this one. You'd have to have some x's of some sort up in the numerator for there to be any x-intercepts. Okay, let's try the next one. So number 2, g of x equals x minus 5 over x plus 3. It does not reduce. There is a 0 in the denominator of -3, so there is a vertical asymptote of x equals -3. The limit does exist as x goes to infinity. It's equally weighted, so we look at the coefficients of those highest powers of x, 1 over 1. So y equals 1 is the horizontal asymptote. X-intercept, x-intercept, if we plug in 0 for the y, Well, again, as I was mentioning, the x-intercept, focus in on the numerator. What makes the numerator 0? 5. And so x-intercept here is 5. Okay, moving on. Last one of these before we start graphing. Number 3, h of x equals x squared minus 6x plus 8 all over 2x squared minus 2x minus 24. Now I'm going to factor this one for us very quickly just so we can save a little bit of time. The denominator has a GCF of 2, and if we do that first, and then factor the x squared minus x minus 12, so 2 times x minus 4 times x plus 3. Okay, so right now we've got 2 zeros in the denominator, 4 and negative 3. However, we always need to check and see if any of them reduce. And so it's important to check the numerator and see, factor that and see if anything reduces. So the numerator factors as x minus 4 times x minus 2. And so we notice that the x minus 4s do reduce. Since it is reducing, it is a 0 in the denominator, but it reduced. So it's not a vertical asymptote at x equals 4. In fact, it is a hole at x equals 4. Ultimately, when we're graphing, we're going to need to know precisely where the hole is. We know it's at x equals 4. But to get precisely where the hole is, we need to know the y value too. So we plug in the 4 into the reduced equation. So 4 minus 2 is 2, and 4 plus 3 is 7, but it's times 2. So 4 comma 2/14. Don't leave 2/14. We always reduce fractions. So 4 comma 1/7. That's where the hole is. Okay, coming back to what we were asked for, though. So we have a hole at x equals 4, but we have a vertical asymptote at x equals negative 3. If we take the limit as x goes to infinity. Now, notice one of the x's reduced out of the denominator here. Here's some general good advice. There has to be at least one x left in the denominator for there to be any asymptotes at all. So in other words, the denominator has to have degree 1 or more, even after reducing, for there to be any asymptotes at all for a rational function. So if both of these x's had reduced out of the denominator, we wouldn't have any asymptotes, period, for this function. You just have some holes in the graph. Now, we do still have x to the first in the denominator, and so therefore, we take the limit as x goes to infinity. You can work with the reduced function, or you could work with the original one, provided you know there's still some x's in the denominator. There are x's still in the denominator. So maybe the non-reduced one, if you take the limit as x goes to infinity, it's 1/2. So horizontal asymptote y equals 1/2. X-intercepts, we do have, if I plug in 0 for the y, if I set this function equal to 0, now much like the fact that a 0 reduced out of the denominator and it was no longer a vertical asymptote, if you have a 0 reduced out of the numerator, it will no longer be an x-intercept. So x equals 4 is not an x-intercept. There's just a hole in the graph at 4 comma 1/7. We do have an x-intercept at 2 comma 0. Okay, now we're going to take advantage of all this kind of stuff, and we're actually going to apply it in the next few problems where we start graphing them. Okay, so graph label all your intercepts and graph the asymptotes too. Okay, so problem number 4, f of x equals x minus 3 over x plus 2. So, negative 2 is a 0 in the denominator. It doesn't reduce. X equals negative 2 is the vertical asymptote. Does the limit exist as x goes to infinity? Yes, it's 1. Y equals 1 is the horizontal asymptote. Might be kind of nice to actually sketch the asymptotes first. These are the framework of the function that we're ultimately sketching. So x equals negative 2. We will be doing a scale for the x-axis and the y-axis this time, unlike when we're doing polynomials. We're doing a scale for the y-axis as well. Asymptotes are not the actual graph. They need to be dotted. You do not do solid lines for the asymptotes. They do show kind of boundaries. Now, however many vertical asymptotes there will always be one more piece of graph than there are vertical asymptotes. This one has one vertical asymptote, therefore there will be two pieces of graph. There will be a piece of graph on the left side of the vertical asymptote. There will be a piece of graph on the right side of the vertical asymptote. The graph will never ever touch or cross the vertical asymptote. Now, let's figure out the x-intercept. We were doing that on the previous problem. X-intercept. So if I plug in 0 for the y, 3, 0. Bless you. So y-intercept. We weren't doing that on the previous problems, but we do need it. How do we find a y-intercept? Don't we plug in 0 for the x? So if I plug in 0 for the x, I get negative 3/2. Okay, let's plot those points, 3, 0, and 0, comma, negative 3/2, 0, comma, negative 1.5. Now, I already mentioned the fact that the graph will not touch or cross the vertical asymptote. Since I have points over here on the right-hand side of the vertical asymptote, let's start on the right-hand side. Now, as it goes towards the vertical asymptote, it doesn't just stop. The graph will keep getting closer and closer to the vertical asymptote without ever touching or crossing, which means, and you guys saw some graphs of these the other day, either it's going to be going down low as it gets closer to the vertical asymptote, or it's going to be going up towards positive infinity. It'll be going up as it gets closer to the vertical asymptote. As it goes to the infinities, as it goes to the left and the right forever, it will go to elevation 1. Whatever the horizontal asymptote is, it's going to that elevation. Now, I have these 2 points. Could I be coming from up high, close to the vertical asymptote, and going through those points and then going to elevation 1? Well, that wouldn't really make sense because we'd have to cross the x-axis to get to that y-intercept. And we've already found all the x-intercepts. Therefore, it cannot be coming from up high and going through those points and going to elevation 1. It must be coming from down low, going through those points, going to elevation 1. Label the intercepts. Okay, now, out here to the left. Could I be coming from down low going to elevation 1 as I go out to the left? Well, I'd have to cross the x-axis, and we already found all the x-intercepts. So no, I could not be coming from down low going to elevation 1 as I go out to the left. Therefore, it must be coming from up high going to elevation 1 as I go out to the left. And there is the graph of y equals f of x. That's a full credit graph right there. Next one. G of x equals 1 over x squared minus x minus 2. Okay, factored form for the denominator, x minus 2, x plus 1. They don't reduce. I've got two vertical asymptotes, x equals 2, x equals negative 1. Does the limit exist as x goes to infinity? Yes, it's bottom heavy, so y equals 0 is the horizontal asymptote. So x equals 2, x equals negative 1, y equals 0. Where's y? Well, y equals 0 is the x-axis. Don't dot the x-axis, however, maybe out to the left and out to the right of the x-axis. Go ahead and dot out there so you remember that it's a horizontal asymptote. Now, anytime the horizontal asymptote is the x-axis, we end up having to plug in more points than normal. So I'll just warn you that that does happen. Okay, x-intercepts. If I plug in 0 for the y, can that fraction equal 0? No, doesn't equal 0. There are no x-intercepts. Now, perhaps you were saying, well, the horizontal asymptote, of course there's no x-intercepts. Graphs can touch or cross horizontal asymptotes. They will never, ever touch or cross the verticals. It can touch or cross horizontals. If it does, it's usually between about negative 10, positive 10, somewhere in there. As it goes to the infinities, it will stay on the one side or the other. But it is possible for it to cross or touch a horizontal asymptote. But we have no x-intercepts in this case, so no, it's not touching or crossing. Y-intercept. Plug in 0 for the x's. We get negative 1/2. Okay, so plot that point. That's the only point we have right now. Two vertical asymptotes, three pieces of graph. You got something out here to the left, you got something out here to the right, and you got something in between the two vertical asymptotes. I'm going to start in the middle between the two vertical asymptotes. Is it possible to be a low to high or a high to low? No, there's no x-intercepts. Therefore, it's either a high to high or a low to low. Well, there's only this one point. It can't be a high to high. You'd have to cross the x-axis. So it's a low to low. It's not a perfect parabola, but it is a low to low. As it goes down, it gets closer and closer to the vertical asymptotes, and it goes through that point right there. Label that negative 1/2. Out to the left and the right, could it be coming from up high going to elevation 0? Yes. Could it be coming from down low going to elevation 0? Yes. How do we know? We have to plug in points, as I was already mentioning. So we're going to plug in something to the left of the vertical asymptote. Vertical asymptote's at negative 1, so maybe let's do negative 2 or negative 3 or negative 10 or something. I don't know. So negative 2 is fine. 1 over, I would get 4 plus 2 minus 2. Now, all we really need to know is if it's above or below the horizontal asymptote. So all you need to know is if it's positive or negative. That is obviously positive. We are above, so we're starting from up high, and as I go to the left, it goes to elevation 0. Now we're going to do a very similar thing out here to the right. because either one is possible. It could be above or it could be below. So if let's see, the vertical asymptote's at 2, so if I input a 3, and all we need to know is if it's positive or negative. So 1 over 9 minus 3 minus 2, which is positive. So we're coming from up high, going to elevation 0 from the top side as we go out to the right. That would be a full credit graph right there. And we have 2 more that we're going to do. So number 6, h of x equals 2x squared minus 8x minus 10. And the bottom is x squared plus 2x minus 3. I'm going to just factor it right now to save ourselves some time. So 2 times x minus 5 times x plus 1 all over x plus 3 times x minus 1. Okay. It does not reduce. We have 2 zeros in the denominator, so we have 2 vertical asymptotes. X equals negative 3, x equals 1. The limit does exist as x goes to infinity. It's 2x squared over 1x squared, so y equals 2 is the horizontal asymptote. Let's see, x-intercepts. If I plug in 0 for the y, I'm looking at how does this fraction equal 0? If x is 5 and if x is negative 1, if they're in the numerator. So 5, 0 and negative 1, 0. Now, by the way, these functions really do not work like the polynomial functions. However, the x-intercepts do work the same. Back in the polynomial unit, if the multiplicity was odd, it went through. And if the multiplicity was even, it bounced. It works the same in this unit. So if the multiplicity is odd, it goes through the x-axis. And if the multiplicity is even, it bounces on the x-axis. These are both to the first power. That's odd, so they do both go through. Y-intercept. 0 for the x's, and I get negative 10 over negative 3, which is positive 10 thirds. Okay, so x equals negative 3, x equals 1, y equals 2. I actually like the ones that don't have the x-axis as a horizontal asymptote a lot better. And you probably will too once you start getting used to it. Plotting points, 5, 0. Negative 1, 0. And 0, 10 thirds, which is 0, 3 1/3. Let's start in the middle. So the x-intercept goes through because the multiplicity was odd. And here's a y-intercept right there. This one has to be a low to high in the middle because the x-intercept goes through and it has to go through that y-intercept as well. Notice we are crossing the horizontal asymptote. I mentioned this to you before. It is possible it does touch or cross horizontal asymptotes, usually between about negative 10, positive 10 is where they happen. Label the intercepts, that's negative 1, that one's 10 thirds. If you're really curious, you could plug in 2, because that's the elevation. If you plugged in 2, and if you solved the function, you could find out exactly at what x value that is, but we don't need to get that. Out to the left and the right. Well, let's do out to the right because we have an x-intercept out there. and its multiplicity was odd, so it goes through. Based on that, it has to be coming from down low so it can go through the x-intercept and continue on towards elevation 2 as it goes to the right forever. Could not be coming from up high, going through and then somehow making its way back to elevation 2, because it would have to cross the x-axis if it came from up high again, somewhere out to the right. So this is the only possibility. Out here to the left, could I be coming from down low going to elevation 2? No, you'd have to cross the x-axis. So it must be coming from up high going to elevation 2 as it goes out to the left forever. Last one. So y equals x squared minus 4 over x squared minus x minus 6. Factored form, denominator x minus 3 times x plus 2, numerator x minus 2 times x plus 2. We have a common factor. Means we have a hole in the graph at x equals negative 2. Specifically, negative 2, and you plug in the negative 2 into the reduced function. So negative 2 minus 2, that's negative 4 over negative 2 minus 3, and that would be negative 5. Don't leave it like that. Negative 2, comma, 4/5 is where the hole is. Okay, since we had a hole in the graph, we only have one vertical asymptote at x equals 3. The limit does exist as x goes to infinity. It is 1, so y equals 1. We have an x-intercept. If I plug in 0 for the y, now remember, if it reduces in the numerator, it's no longer an x-intercept. So we only have one x-intercept at x equals 2, so 2, 0. Y-intercept, plug in 0 for the x's, negative 2 over negative 3, in other words, positive 2/3. So x equals 3, vertical asymptote. Y equals 1, horizontal asymptote. X equals 2 is intercept. Y equals 2/3, or 0, 2/3 is the y-intercept. And don't forget about the hole. The hole is negative 2, 4/5. How do we graph a hole? Put a little hole at negative 2, 4/5. Since all the points we have are out to the left of the vertical asymptote, let's do that part. I hope it seems rather obvious that you're coming from down low next to the vertical asymptote and going towards elevation 1 as you go out to the left. Don't draw a line through the hole. Bring it up to the hole and then pick it up on the other side of the hole. Label your intercepts. 2, the y-intercept is 2/3. Label the hole. Negative 2, 4/5. Okay, we have our last piece on the right-hand side of the vertical asymptote. Could it be coming from down low going to elevation 1? No, because it'd have to cross the x-axis, and we already have all the x-intercepts. Therefore, it must be coming from up high going to elevation 1 as it goes out to the right. Okay, so now you would do worksheet 6A.